in lecture 25, we talk about the temperature dependence of conductivity. This is only a partial lecture. So in this lecture, we talk about the temperature dependence of intrinsic carrier concentrations, and we followed up with the three temperature ranges in temperature of carrier concentration in an extrinsic semiconductor, and we talk about the temperature dependence in each of those zones. So the first thing is to identify the three temperature regions for majority carrier concentration in a doped semiconductor. Intrinsic, saturation, ionization, these are the three temperature ranges corresponding to high, medium, and low temperatures. So first, let's look at the intrinsic carrier concentration. This is the equation that we obtained previously. The intrinsic carrier concentration depends on the square root of the effective density of states in conduction band and valence band, but more importantly, we have this e to the minus eg over 2 kT dependence. NCNV does have a weak temperature dependence, t to the 3/2, but the most of the temperature dependence comes from this exponential term. So if you take the logarithm of n sub I, you get to a sort of the constant. It has a weak temperature dependence, but that we can neglect that. But more importantly, we have this Eg over 2 kT. So if you plot log Ni as a function of 1 over T, you should expect to receive a straight line, as you see here. For these different semiconductors, you see the intrinsic carrier concentration in the log scale does have a sort of linear dependence with 1 over T, and the slope is really given by Eg over 2K. Okay, so and it's a reducing term, so the slope is negative. And for smaller band gap like germanium, it will have a high intrinsic carrier concentration at room temperature, but it goes up more slowly. When you go to greater band gap materials, you see a suppression of intrinsic carrier concentration at room temperature, but as you go to higher and higher temperature, they will rise up steeper. So for silicon, at room temperature, you only have 10 to the 10th per cubic centimeter intrinsic carrier concentration. When you go to 1,000 Kelvin or 700 degrees C, it'll rise up by 8 orders of magnitude to 10 to the 18th per cubic centimeter. So at room temperature, this is sort of the medium temperature range. We can assume all impurities are ionized. So for N-type semiconductor, the doping concentration typically is going to be much greater than the intrinsic carrier concentration. So we have these extrinsic carriers dominating, and the electron concentration is mostly going to be given by the doping concentration, the donor concentration. And so that's actually temperature independent. It's saturated to whatever doping concentration you put in. But the whole concentration is going to be temperature dependent because Ni, the intrinsic carrier concentration, does depend on the temperature. And then the Fermi energy location depends on temperature as well. This ratio is constant, and means that EF will be linear with the temperature. So that's for the medium temperature range, and mostly room temperature is part of this range. And the important thing is that all impurities are ionized. When you go to higher temperature range, we know in the previous slide that the intrinsic carrier concentration will increase exponentially. So that could possibly get to a situation that the intrinsic carrier concentration is much more than the donor concentration you put in. So in that case, the intrinsic concentration may actually take over. And in that case, even though the impurities are ionized, we still have much more intrinsic carriers than the extrinsic carriers. So in that case, it behaves as if we only have intrinsic carriers. It's dominating. Okay, so the Fermi energy is going to be somewhere in the mid-gap location, and the intrinsic carrier concentration is going to be given by this e to the minus eg over 2 kT behavior. When you go to lower temperatures, then the assumption of all impurities are ionized have to be re-examined. Actually, in that case, if the temperature is not high enough, even though the binding energy of those donor impurities, donor states are very low, on the order of tens of million electron volts. When the temperature is really low, then this could become more than several kT, and that will limit the probability of these electrons to be excited into the conduction band. So in that case, not all impurities are ionized if the temperature is really low, and in that case, some of these impurities are just going to remain neutral. Okay, so in that case, we are going to have fewer extrinsic carriers in the conduction band in the N-type situation, or if it's a P-type situation, then we are going to have a few extrinsic holes in the valence band. In that case, you have so-called ionization temperature range. So that's a qualitative delineation of the three temperature ranges. But now let's look at the temperature dependencies of each of those three temperature ranges qualitatively and quantitatively. So this is sort of general behavior. Looking at the intrinsic range, we have the electron concentration. This is using the example of N-type semiconductor. The electron concentration has a exponential dependence as a function of 1 over t. So pay attention to the scales of this axis. We have a log scale in the vertical axis and the 1 over t, the reciprocal scale on the horizontal axis. So in the intrinsic temperature range, we have this e to the minus eg over 2kt dependence. So the slope is given by minus eg over 2k. Then we have this immediate temperature range, in which case the majority carrier concentration is constant. It's only given by the doping concentration, so it doesn't change with temperature. Okay, and in the ionization range, we have again the carrier concentration depends on e to the minus delta E over 2kt, and this is because we are ionizing the electrons from the donor impurity states to the conduction band. So this delta E is a binding energy of those donor impurities. Yeah. And so again, with this e to the minus delta E over 2kt, you're going to be seeing a sort of a straight line in this log 1 over t plot. But the slope is given by delta E, and this delta E is the impurity binding energy, which is going to be much smaller than band gap. So the slope is going to be a lot shallower than in the intrinsic range, but it's still a straight line. Now, one thing I do want to mention is that both this middle temperature range and this lower temperature range, the carriers are induced by these donor impurities, all except impurities in the p-type situation. So both these temperature ranges are actually due to extrinsic carriers. So in the textbook, the author called this middle temperature range as extrinsic. It's not very appropriate because the ionization range is also contributed by these extrinsic carriers from the donor impurities. So the more appropriate name for the medium temperature range is actually called saturation. That is, the majority carrier concentration is saturated. Okay, so make sure that you call this saturation, not extrinsic. That's the end of lecture 25 review.